Hello everyone, and thank you for joining me in this video short where we are going to discuss the convex hull problem. A convex hull is a polygon that encapsulates a shape, a set of points, or something similar. And so the general problem here is that we want to find the smallest convex polygon or polygon that will encapsulate a shape or these sets of points. There are all sorts of applications of convex hulls, convex combinations, and convex models in data science applications and in optimization. So let's go ahead and dive in and get started here. Again, some great applications to data science include modeling of data using linear systems. Again, if you view points of data or data points in some space, right, the extreme points can be used as a linear model if you are using a convex combination of those points to represent all of the points that lie within the convex hull or sort of in between those bounding points. Also used in data fusion models. Convex combinations are used quite a bit there as well. And then convex optimization as well, using a convex hull to model or bound a feasible solution space or something similar. So again, great applications to data science here. And so you might be asking yourself, what is a convex hull? Right, so again, here's a great example of a convex hull shown with the blue edges encapsulating data points shown as black dots. And so you know that we have a convex hull if we draw any arbitrary line through the point cloud, it will intersect with the convex hull exactly twice. So here we have a convex hull, right? And here we do not, right? Again, because we have more than two intersections. Again, the general idea here is that we want to find not just any arbitrary convex hull, but the smallest convex polygon, the smallest convex hull that will encapsulate all of the points. So that means that the points might lie on the convex hull itself, right, or be very near to them. So the basic idea here, or at least conceptually speaking, is you want to think maybe starting off with some sort of rubber band, right, starting from the outside and working your way in here. And so they'll get sort of stuck on the outer points and then create this convex polygon that'll encapsulate the entire point cloud or set of points. All right, so how can we solve this problem? Well, you can think of this again, as with many computer science problems. Let's start with a brute force approach. And so you could think of all possible edges. You could start with a fully connected graph and start removing edges and look at all combinations of all possible graphs. That would be very inefficient, very slow. Another brute force approach that's slightly more efficient would be to solve this problem here with each pair of points. That is, if you look at a pair of points, you draw a line or create the line that is defined by those 2 points. If points in the point set lie on both sides of the line, then those points are not on the convex hull, right? And so if we repeatedly do this for all pairwise points, we can get the convex hull, and we can do so with a cubic runtime. That is, we will have a big O of n cubed. So that is one way to solve this problem. However, there are many other ways to solve this problem as well. And so I encourage you to continue through this slide deck where we identify a number of different algorithmic solutions and approaches to solving the convex hull problem, each of them getting more and more efficient until we identify that we can actually reduce this problem to a sorting problem, meaning that we can solve it in n log n time. All right. Well, thank you for joining me in this video short, and I'll see you in the next episode.